Yeah, thank you all for giving me the opportunity to speak. Um, yeah, so let me get into the reasons for this project. So my goal was to generate, I guess, like LiDAR data that consists of raster that's just covers an individual county. Um, and the reason for this project, or the main idea that kind of sparked my recognition of a need for techniques to generate data in this format, was I had the opportunity to visit the Arsberger site for the first time, which is pretty close to where I grew up, and I've been interested in it since I started working in cultural resources, because it's one of the archaeological sites that contains a fortification ditch, a pretty extensive fortification ditch complex that is visible. So I was really excited to get out there, and once I was out there, I realized, wow, this is actually a pretty subtle feature. It's very easy to see, you know, in LiDAR data, but you know, I thought to myself, like, wow, if I was, you know, out in the field surveying, this is something that I might miss. And I don't know what that says about me as an archaeologist, but I thought we need better background data, you know, for our office. And I knew, so I work at the Archaeological Research Center in Rapid City as its GIS coordinator, and I knew that we only had LiDAR data for probably half the state, or LiDAR Hillshades for about half the state. So there's, you know, half of the land that we could potentially be charged with doing an archaeological survey on, we wouldn't be able to review using LiDAR Hillshades. And so, like, after I went out on this, I was thinking to myself, all right, I've got to fill the holes at least in our data, just to make sure that we don't, you know, miss something that would be obvious otherwise. And I wanted to stick with the precedent of dividing the rasters up by county, just because that's the format that people have used in our office, going back to before I was there, and is kind of, I think, standard, fairly standard across the industry. And just to give you, in case you're not really aware of LiDAR, I suppose I should explain what it is. So LiDAR stands for light detection and ranging, and it involves a flyover or an airplane with surveying related equipment that shoots lasers at the ground and measures the speed of return to then, with the airplane's altitude, determine the elevation of different parts of the landscape. But it can be very high resolution data. I think in some data sets that I've seen, there's an elevation point collected for every 30 centimeters of space. So it can represent, you know, microtopography, I think, across the landscape. And it helps with, its archaeological utility is that it helps with identification of cultural features like historic forts, wagon trails, burial mounds, earth lodge depressions, of course fortification ditches, and it can also help with identifying landforms and landscape position. And you know, one landform that's associated with archaeological sites, or highly associated with archaeological sites, is stream terraces. So it can help with identifying those too. So here are two examples, and Aaron, you may find these examples very familiar. Aaron did an article either a year or two ago related to using LiDAR to locate archaeological resources. And this right here is Fort Sully near Pierce, South Dakota. And you can see the outline of where the edge of the fort used to be that I'm tracing with the laser right now. You can also see some of the places where there used to be walls of structures within the fort using this DEM colored hillshade. This fortification ditch is very apparent in this data, but once you get out there, it can be kind of difficult to discern, especially with the grass being fairly long. So to begin the process of creating data for what I thought was going to be half the state going in, I knew that I needed what's called a tile index, or I needed a lot of tile indexes, and I wanted to combine them just for ease of use. So these are grids that are usable in geographic information system software, where basically the cells of the grid are associated with a specific tile index, associated with a specific tile name. And that tile name, if added to a file path, or a URL, will allow you to create links to downloadable data that's accessible through the USGS's website. So what I did was I combined all these tile indexes, then I added fields to some of these tables that are accessible in ArcGIS associated with what are called feature classes, which is just quite a few polygons, usually consists of quite a few, features. Then after those fields were created, I populated them, using the tile name to generate URLs. And I created URLs for what's called LAS data, which is just a LiDAR point cloud, so a bunch of point features, and then also to TIFF files. And the TIFF is just a file format for a raster, so like a geospatial cell-based data set. And the federal government now makes these TIFFs, pre-processed LiDAR data, available to the public. So it's easy to get now. It didn't used to be that way just a few years ago, but now they have TIFFs generated for almost all of the tiles that they have classified in their various tile indexes. So let me talk about the specifications of the computer that I was going to use to try to complete this project. It's a pretty good, it's about as good of a personal computer as you can order. So I had about 4 terabytes of storage, 128 gigabytes of RAM, 3 gigahertz processor that's like one of the newer generation processors, an i9. I think it has like 24 cores, I want to say. And a Windows 11 operating system, and I was using ArcGIS Pro version 3.3.2. So I decided fairly early on that I decided to use the TIFF files that were available, or to try to focus on using the TIFF files. And the reason for that is because it requires a lot of storage space to process LAS data, the point cloud or LiDAR related point cloud data, into these rasters, or digital elevation model rasters. And I wanted to avoid investing more time into filling the holes in our data than I would have to accomplish generating something that was effective enough to perform an archaeological review. So I focused on using the half-meter resolution TIFFs that the federal government makes available for, I think now, the vast majority of South Dakota. And these wound up generating DEMs without seams when they were tied together, and they were basically almost identical in most cases to DEM produced with LAS data. So this is a procedural overview. This is how I created ultimately the Hillshades. First, after generating this massive tile index that covered the entirety of South Dakota, I selected all those tile polygons in ArcGIS Pro, and then I exported the selected records to, for a specific county, so that's important. So I selected all the index polygons within a county, then I exported the records to an Excel table, so that way I could copy the TIFF URLs. And following that, I used this software called UGET that's accessible through the USGS's website to download the necessary TIFFs. So you can download them all together. There was, I think, one of the bigger counties was Perkins, and that had close to, it's either 7,000 or 8,000 separate TIFF files, which occupied maybe, I don't know, either 100 or 200 gigabytes of space on my hard drive temporarily. So UGET is a great tool, and I think it only took maybe an hour for it to, or maybe less time than that, an hour or 30 minutes to download all those TIFF files for Perkins County, which is the second biggest county in the state. Following downloading all those TIFFs, I then performed a series of merges and mosaics, and then finally clipped the merged TIFF file by the county boundary to then create a county 1 meter DEM. I also resampled the half-meter data into 1 meter data, because that reduces the amount of cells in a raster by a factor of 4. So that helps with storing this data effectively. And really, for like larger archaeological features, I think that the half-meter resolution data, it probably wouldn't help that much with, say, burial mound identification, but it might help you see something like, a sunken-in former location of a cache pit. I've seen that kind of thing, but just because I wanted us to be able to do, a more broadly focused archaeological review with this data, that really didn't seem all that necessary to, and a lot of the data that we had available was also in a 1 meter cell size. So that kind of set the precedent for what I sought to do. And then following creating those DEMs, I generated Hillshades with them. And that's probably what most people are most familiar with, just because it's one of the more user-friendly forms of LiDAR data to use. So when people, like someone that isn't really GIS focused talks about LiDAR, I just, Hillshade, I think Hillshade. This is a graph of how long it took to generate county DEMs with different processes. And I played around a lot with different ways of generating them, because I was trying to kind of do this in the background of my other tasks that I have to do throughout the day, and I didn't want this to be a big, drain on my productivity. So I kind of wanted something that I could maybe have like somewhat automated, so I wouldn't have to be clicking away to coax this process along. I know how to code Python, so different Python packages that could generate DEMs were an open option for me. So that's what this GDAL package was. It was something that I could basically download in my integrated development environment, and the one that I am most familiar with and use is called PyCharm. And that package produced rasters the quickest by far. I couldn't believe it when this Hanson raster, or raster for Hanson County, was kicked out in, I think it processed it in 30 seconds. Austin Buda might remember when I was working at Augustana in like 2021 or 2022 and trying to make a Minnehaha County digital elevation model. I let that thing run all weekend to produce it. So this is like, I mean, I was just amazed. I didn't believe it. And I thought it was probably corrupt, you know, like it didn't produce the file correctly. And then I opened up ArcGIS Pro and looked at the raster and thought, holy cow, it did it in 30 seconds. How did it do that? Yeah, sure enough it did. But then I found out that they have made massive improvements to ArcGIS Pro as well. You know, so if you look at this, and I should mention, when I was creating those digital elevation models, you know, maybe 4 or 5 years ago, those were I was using the LAS and LAS data, so that added a lot of time to the process. But yeah, you can see from this graph that GDAL was the quickest process. It cut, I think, the ArcPy generation time in half, but really, I mean, Perkins is the second biggest county in South Dakota, and through downloading all the TIFFs for Perkins County and running them in running them in ArcGIS Pro, I was able to create a Perkins County DEM in just basically 20 minutes. And I just put them directly into the graphical user interface, into the Mosaic tool, or Mosaic to New Raster tool, and it just kicked out a Perkins County raster. I guess it did have like one small error, but I'll talk about that later on in the presentation. But yeah, you can kind of see the breakdown. I also tried to use QGIS. Maybe some of you have heard about that. That's a free open source software, GIS software with a user interface, a lot like ArcGIS Pro. And that had more problems with freezes and hangups, and I'll talk about that. So you can also see here that the trend here is the more rasters, the more, you know, federally available TIFF files associated with their tile index you put in, the longer the process takes, obviously. So, and I think it might, you know, it might be getting, or you might get diminishing returns at a certain point. Yeah, that covers it. So this is that Hanson County DEM that I produced, and you can see from the elevations that they make sense, and the blues represent lows and the white represents highs, and you can see drainages nicely. Yeah, so a pretty good looking DEM. So the pros and cons of available software packages, I think break down like this. So QGIS results in the slowest DEM generation, and it crashes installs often. There were, early on I was trying to use this software because I thought it would accelerate the rate at which I was able to produce DEMs, and what would end up happening is I would try and run QGIS and then be mapping, you know, or creating maps in the office, kind of letting QGIS run in the background, and then everything would freeze. And then I wasn't even able to shut down my computer normally. I just had to like hit the power button, you know, watch my computer shut off, and then start fresh. Rasturio was another Python package that I tried using, and that was crash or stall resistant, but it was really finicky with input data. Like, it didn't like when I put rasters, federal tile TIFF rasters in that were collected during different flyovers, even if they were in a common coordinate system, which was frustrating. ArcGIS Pro had quicker processing than QGIS or Rasturio, but it did kind of, I would say it stalls more often than it crashes, but, and I sort of wrote it off early on as a technique for generating, you know, what became 66 DEMs that cover all the counties in the state of South Dakota at a 1 meter resolution. But after revisiting it, I realized it would have helped if I was just a little more patient with it. and didn't give up on it. ArcPy, pretty much, I think it uses a lot of the same processes as ArcGIS Pro. It just takes away the graphical user interface, and for that reason, that's, I think, why it's more crash and stall resistant. I don't think I ever had my computer freeze or stall when I was using ArcPy for ArcPy's Mosaic function. And with GDAL, it had the quickest processing, but the result was, or the resulting rasters were uncompressed, so they were about twice the size of what ArcPy and ArcGIS, or ArcGIS Pro would produce. But that wound up being an advantage because after I produced these rasters, they had to be checked for quality. So, you know, before finalizing them, like, why would I want every single one to compress every time I generate one? I would rather wait until I have the raster the way that I want it and then compress it in order to have a good final product that I didn't spend extra time creating than was necessary. So this is the GDAL portion of DEM generating Python code, and it really, like, so here's a for loop. This indicates that, this is just generating raster file paths and adding them to a list. And then this is just a message that it gives me to let me know where in the code or what part of the code is currently running. Then with this, I'm just having it not give me a bunch of warnings. Here I'm setting how much RAM the tool can use, and here I'm giving the tool, you know, what kind of file it should produce. So geotiff, I want no data to be assigned a value of -9999999. Just for simplicity, I don't think anywhere on Earth is that low, and that's why that number was used. And here's the cell resolution for X and Y, and then resampling. If, like, you're converting from one coordinate system to another, the raster will have to be resampled. And then this is really just the command that runs everything. Just one command produces a massive DEM. So following DEM generation, these were the review methods that I used. I wanted to make sure that the DEM had sensical elevation. So if a portion of Perkins County's DEM had a value of -0.3 meters above mean sea level, that isn't right. Like, there's no place in Perkins County that should be that low unless it's like a huge, you know, strip mine, like open cut thing. So I knew that, and I'll show you later, that one of the ones that I produced for Perkins County was screwed up, but it wasn't too bad to fix, considering the size of the raster. And yeah, check for a 1 by 1 meter cell size, check for correct coordinate system, you know, where, like, South Dakota is split between zones, UTM zones 13 and 14. So, you know, where that split happens, I wanted the coordinate system associated with rasters to be tied to where the county's larger proportion, you know, the UTM zone that the county's larger proportion resided in. And then I wanted to check for resampling errors. I wanted to make sure there were no resampling errors. There were a few DEMs that generated with, like, jagged roads on, you know, one side of the coordinate system line, and that's because the resampling didn't work effectively. But just kind of doing the DEM generation in 2 chunks resolved that. And then I wanted to check for full county coverage. So nonsensical elevations, how I fixed those involved isolating values with raster calculator. With this tool called the con tool, it's pretty easy to just code a raster with either a 1 or a 0 based on the elevation range that you specify. And then after identifying where the rasters were screwed up, I sought to overwrite the raster with new raster data that usually came from LAS data that's federally available that I could process without the error. or to exclude the error. And then coordinate system-based resampling errors were also present, and yeah, as I mentioned before, separate processing by like separating the rasters by coordinate system, and then merging or mosaicing just two final files. I think I usually use the mosaic tool in ArcGIS Pro to do that, and that seemed to not result in the resampling errors. So here is a raster calculator window opened in ArcGIS Pro, and you can see here that one of the values is negative 0.3 meters above mean sea level in Perkins County, which is, I thought, obviously wrong. And then after doing that, you know, this raster calculation, that produced a raster of ones and zeros, and I think here these represented polygons were zero related cells in the raster, and I just converted raster to polygon for simplicity of symbolizing. So that's what you see here. So I knew like the tile that's associated with this polygon and the tile associated with this polygon need to be downloaded, or the LiDAR point clouds need to be downloaded for them. Then I need to decompress the point clouds. Then I need to generate a raster from LAS data for the tile, and then splice the tile in. And yeah, and it resulted in raster without errors, as far as I can tell. And the next step then, after putting together a viable set of county-wide DEMs, and because I discovered that this process was going so quickly, I thought, well, I'll just generate them for the entire state. So I did created a 1 by 1 meter DEM for every county in South Dakota, just so they were all consistently had consistent specifications, and then I ran this code, and this code ran overnight to compress all 66 of those viable DEMs into, you know, 1/2 about usually of the size that they were initially. And this is really a simple bit of code too. It just takes the raster file path and strips the county designator from it, and then slaps underscore DEM.tif onto it, and then it just copies it. But the way that it copies it is using ArcPy tools, and those just kind of auto compress everything. So and I changed no data values to their no data standard, and then generated pyramids and calculated statistics for it, so that way when you bring it in, you don't have to wait for the software to do that, and that was it. And then following that, that was when I generated Hillshades for everything. And this portion is wrong. I just excluded the first one here. I should have changed this before I copied it. But this should have a 0. So that way it would, you know, cover. And I just did 70 because I couldn't remember. Was it 65 counties or 66 counties? Because it had stopped running as soon as it runs out of things in the list to generate Hillshades for. And so I generated Hillshades from, so Hillshade is a raster that symbolizes the landscape using shading that kind of makes sense based on a particular position of the sun, in this case 45 degrees, if 0 degrees is north, and 315 degrees as well for a separate raster, so you can kind of use them in contrast. And then I figured out that you can actually generate multi-directional Hillshades as well using Python. And so this was another bit of code that I let run overnight to generate all of the Hillshades that I wanted to. And then built pyramids and statistics for all of them. But the DEM command, or the multi-directional Hillshade command is a little different than the other commands in that you have to, I think, create like a Hillshade output object and then call one of its, and Greg knows this better than I do, I think this is like, is it a, shoot, not a function, but one of its abilities, I don't remember what the term is, to save it. So it's a little different than just like calling the Hillshade tool, you know, in 3D Analyst and producing one. Okay, and these are the results. Here is the multi-directional hillshade. This is the traditional hillshade, and you can see that the shadows are pretty bad in this. This helps. But this is better for like identifying things up on the flat, I think. The shadows are more exaggerated, but this is better if you want to actually see the relief on a hill slope. So to have them both is helpful. This is colorized DEM. And so my conclusion is that GDAL performed the quickest of all raster merging and mosaicing software packages tested in this project, but ArcPy and ArcGIS Pro are workable options for statewide 1 meter DEM generation. So if you don't code, please don't be discouraged. You can have one of the tools in ArcGIS Pro generate a mosaic from 1,000 or 7,000 rasters. Yes, and this is encouraging for smaller research institutions and firms, or just like small academic departments. Multi-directional hillshades can be generated systematically to supplement DEM interpretation, and that is all I've got. Yeah, thank you for your time.